This is Shanaka. Thanks, Manav and Suresh. We started our model building with two convolutional layers and we achieved 63% accuracy, which was not that satisfactory. So we decided we need to go deeper. Transfer learning is one of the techniques used in machine learning, just solving one problem and applying the knowledge to a different but related problem. There's usually insufficient data to train a model from scratch, and it takes a lot of computational power to do so. It could take weeks to train a modern CNN across GPUs. Following some of the popular models used recently, like VGG16, Google Night Inception, V3, V4. So for our solution, we'll be using VGG16 model and we'll be fine-tuning it. This is named after the Visual Geometry Group from Oxford, and it used to win the ImageNet competition back in 2014. It has 5 layers of convolutional blocks and 1 fully connected layer. So this is the overview of the proposed model. We have 5 blocks of convolutional layers, which is coming from VGG16, and on top we have our fully connected layer. This is the strategy we'll be using. We are going to initiate the VGG16 model with ImageNet weights, and then we're going to extract and save bottleneck features out from VGG16. We're going to load our saved data and train a fully connected model on top of that, and we're going to call it top model. We're going to create the full model combining the VGG16 with the top model. Then we'll be initiating the convolutional phase of VGG16 and load its weights. We're going to load the top model weight saved in step 3, and we're going to freeze the layers up to convolutional block 4. Finally, we start training the full model with a very slow learning rate. Alright, let's dive into the code. We'll be using TensorFlow and Keras for a solution, and we are setting up the Conda environment, and we'll be using these Python packages. So after we install Keras, we can check which backend we'll be using. So you can use TensorFlow, and you can change the configuration if you so, we'll do so. But in this case, we're not going to do anything. We're going to verify the GPU. So in my case, I have a GPU with 2 GB of RAM, and so we can prepare our data. We're going to see it as the train and test data sets into HDF5 format. So this script is going to create the H5 file, and the one below it's going to create another one for the training data set. Also, it's going to create the one-hot features. So after that, those scripts run, we can see those 2 files, and we're going to verify our labels. And so here we can see we have the one-hot encoding in our dataset. So as mentioned earlier, we started building with the 2 convolutional layers, and this is it. Then we explained a few other models, and finally model 7, that is the best performing model. So we discussed the strategy we are going to use for building this model, and this is the TensorBoard graph for the model 7. So here we have the sequential top model and the VGG16 model down here. So we are going to import all these packages, and we are using TensorFlow backend. Here this function is going to load the training dataset, and this one's going to load the test dataset. Some global settings, we will be using epochs 3, batch size 3, and this is the bottleneck feature file. So first step is we are going to save the bottleneck feature, and this function is going to load the VGG16 model with ImageNet weights, and it's going to save the bottleneck features to that file as an NumPy array. Next step is training the top model. So we'll be using the NumPy array saved earlier, and we are going to feed it into our top model. So then here we fit the model, and then we save the weights that model down here. And here we are building the full model, combining the top model and the VGG16. So here base model we have the VGG16 and top model. Here we load the weights that we saved earlier, and here we combine those two models, base model and the top model. Here we are tracing the weights up to convolution layer 4, so those will be untrainable, and then we'll be using Adam optimizer with a very low learning rate. Here we split the datasets into test and train and validation, and we are fitting the model down here. Next we are predicting the so here you can see we are going to use the submission file and saving the prediction. So recently Kaggle added additional test dataset, so that's why we have two blocks here. And execution. So we set all these variables and call in the save bottleneck feature. So we can see the model summary here. We have 5 blocks of convolution layers, which is coming from VGG16. And once that script executed, it took 1837 seconds, and it saved those two files. Then we train the top model. We are using 2 epochs, but ideally we should at least run 10 epochs. Since this model is very small, it's going to only take 58 seconds, which is good. And then we are going to save this weights from the fully connected model. Next, we are going to train the full model, combining the last two. So we call the train full model method, and so here we only use epoch 1, and then next step we are going to change the test size to 0.1 and run that same method again. And so here we can see trainable parameters 9.1 million and non-trainable parameters 0.3, because we for some of the layers. So once that is done, we can see the accuracies. It goes up to 0.96958, which is good. And then it's generating the predictions and saving to that file. So once those epochs done, we can see this weight file and the model 7 submission CSV file, so we can submit it to Kaggle. And the performance of our model. So there were 2 data sets we discussed earlier. There's high resolution TIFF images with 4 channels and 64-bit, and low resolution JPEGs with 3 channels. So we used the JPEG dataset and we downsized images to this size because we only have limited time constraints and hardware constraints. But even though we use 1/10 of the data provided, we were able to secure top 14% of the Kaggle leadership board. So that's a good news, and currently we are in 30th place in the Kaggle leaderboard. And the future work will be integrating the infrared channel, and also we are planning to use the high resolution TIFF images, and we are planning to use more color correction and augmentation. So performance benchmark. So to train the model, it takes about 8.25 hours. So that's why running these models are very computationally intensive and expensive. So, and this is just using 1/10 of the data available. Conclusion: we built a CNN model using VGG16 for satellite image classification. We use TensorFlow, Keras, and Python. Utilize Google Cloud. We utilize GPUs for computation, and we achieved 30th place on Kaggle leaderboard. Thanks for watching.